Hello students, welcome back. In this part, we are going to discuss about hexagonal close packing and cubic close packing. And we are also going to discuss about the concept of coordination number. So let's start. Now we will see the three-dimensional packing. So in the previous part, we have seen we have arranged one layer, and above that we arranged one more layer, and we got tetrahedral and octahedral voids, and we learned about the tetrahedral voids as well as the octahedral voids and how they are formed. Now in how many ways you can put the third layer over the second layer. Okay, so if you put the third layer over the second layer, what happens? How many possibilities, in how many ways you can put? Let's see. When the third layer is placed above the second, there are two possibilities. You can put it in three ways. You can put it in two ways. So first is covering the tetrahedral voids. So by placing the second layer on the first layer, we got tetrahedral voids, right? And we also got octahedral voids. So if you put the third layer in a such a way that it covers the tetrahedral voids, you will get one type of arrangement. So that is AB type of arrangement, and the structure, the crystal structure as a result will get is hexagonal close packed structure. So instead tetrahedral voids, if we cover octahedral voids, we will get a different type of arrangement, that is ABC type of arrangement, and which will give us CCP. CCP means cubical close packed, or FCC, that is face centered cubic structure. Both are same. FCC is same as CCP. Okay, so two possibilities we have. So you can put the third layer over the second layer in these two ways, covering the tetrahedral voids as well as octahedral voids. So let's first see the tetrahedral voids, how we can cover the tetrahedral voids and how we will get HCP, hexagonal close packed structure. So hexagonal close packing, HCP. So it has AB type of arrangement of layers. That means A, B are the two layers. The third layer is exactly equivalent to the first layer. So that's why the third layer is also given a name A. And the fourth layer is exactly equivalent to the second layer. So fourth layer will be B. So AB, AB, AB and so on. So such type of arrangement is known as HCP. So where you can see this is A and this is B layer, and if you put the spheres of the third layer in a such a way to cover the tetrahedral voids, whatever the arrangement of the third layer will get, that is exactly similar to the first layer. Okay, so that's why the same name is given. So A, we call the third layer as A because it looks exactly similar and same as the first layer. Okay, so AB type, where you can also see here AB type of arrangement will get. So it has a pattern of spheres repeated in alternate layers. The tetrahedral voids of the second layer may be covered by the spheres of the third layer, which we already seen. So if we put in a such a way that the third layer covers the tetrahedral voids, the spheres of the third layer are exactly aligned with those of first layer. So that's why the third layer is given the same name as the first layer. So AB type. So some of the examples which crystallizes in HCP is magnesium and zinc. Magnesium and zinc has a HCP structure. Okay, so let's learn more about it. Hexagonal close packing. So here if you see, this is the unit cell, HCP unit cell looks like this. So we have 6 spheres or 6 particles at the corners of the hexagon, and we have one at the face center, one at the center of the face. Okay, so total here we have 3 plus 3, 7 particles at the bottom, and we have 3 particles which belongs entirely to the unit cell, and above that we have exactly similar arrangement as shown below, right? This is A, this is the first layer A, and this is second layer B, and this is the third layer which is same as the first layer. Okay, so this is the unit cell and this is the space filling model, where the 3 atoms 1, 2 and 3 they entirely belongs to the unit cell, and this is the hexagonal close packing. So if you calculate the number of particles per unit cell, you will get 6. Okay, let's see how you will get 6. How hexagonal HCP unit cell contain 6 particles effectively. So here we have corner particles. So let's see contribution of the corner particles and how many corner particles we have. So total we have 12 corner particles, right? 12 corner particles, and each corner is shared by how many? Each corner is shared by 6 HCP unit cells. Okay, so each particle has a contribution of 1 by 6 into total we have 12. So we have 2 particles effectively from the corners. And let's see the face centers. So face centers, if you see the face centers, we have this particle which is shared by 1 which is present below, right? So its contribution is only half. So half into 2, that will get 1. Okay. So now let's see, these 3. Since these 3 particles belongs entirely to the unit cell, we have 3 more particles. So 3 plus 1 plus 2, total we have 6 particles per unit cell. So HCP unit cell contain 6 particles. So this is about the structure of the unit cell of HCP and number of particles it contains. Where you can also see in this picture. So let's see a video demonstration on hexagonal close packed structure to understand it even better. So hexagonal close packed structure. This is the unit cell contain 1 atom at each corner. So you can see this is the first layer, second layer, third layer, fourth layer. Okay, the first layer is exactly equivalent to the third layer, right? Where you can see here, this is the first layer and the second layer is placed on the first layer. So this is layer A and this is layer B, and these 3 particles belongs to the, these 6 particles which are in the first layer, in the layer A. So this is one face centered particle, and all other 6 are placed at the corners of the hexagon, and these 3 particles belongs entirely to the unit cell. And if you put the third layer to cover the tetrahedral voids, this layer, the third layer is exactly equivalent to the first layer. So we'll get AB type of arrangement. AB type of arrangement you will get. So let's see the coordination number. So listen to me carefully here, the coordination number. So coordination number is the number of nearest neighbors, right? So number of nearest neighbor is the coordination number. So if I take a particle, that particle is in touch. Okay, let's take this particle. Okay, so this particle is touching with this 6 spheres, right? So 3 plus 3, 6 spheres. So it is touching with the 6 particles in its own plane, and this is also touching with the 3 particles which are present in its below plane. This is one particle, this is one more particle. So this is touching with 6 spheres in its own plane and 3 particles which are present below its plane and 3 particles above its plane. Okay, so this particle is total is in contact with the 12 particles. So its coordination number is 12, right? So each particle is in contact with the 12 particles. Out of 12 particles, 6 particles are in its own plane and 3 above its plane and 3 below its plane. So the coordination number of HCP is 12, right? The coordination number of HCP is 12, and let's see that this is the unit cell. The unit cell of HCP, you can see we have particles at the corner and each is having a contribution 1 by 6, and we have at face center at the 2 hexagonal faces, and we have we have 3 particles which belongs entirely to the unit cell, and the total number of hexagonal the total number of particles in HCP unit cell is equals to 6, that we already derived. Okay, so this is all about the structure of HCP. I hope that you clearly understand each and everything in HCP unit cell, which has AB type of arrangement. So let's move to ABC type of arrangement, that is cubical close packing structure, CCP or FCC. So it has ABC type of arrangement of layers. First layer, and we have second layer, and the third layer we placed to cover the octahedral voids, right? The third layer may be placed above the second layer in a manner such that its spheres cover the octahedral voids. So if you place the third layer in such a way, the third layer will be entirely different from the first two layers. The third layer will get is entirely different from the first two layers. So that's why a different name is given. So we call this layer as C. Okay. So C, and if we put the particles above the layer C, we'll get exactly similar, exactly first layer, same as the first layer. So that's why the fourth layer has given a name A. So if you place above, we get B, C. So here, from here, the pattern is repeated, right? So A, B, C, and after C, above C we have A, and above A we have B. So A, B, C, A, B, C, this type of arrangement is then repeated periodically, okay? So such type of arrangement is known as CCP arrangement. Yeah, only when fourth layer is placed, its spheres are aligned with those of first layer, okay? So this is the unit cell of CCP unit cell. Yeah, we have particles at the corner, and we have particles at the face centers, and we have, yeah, at corners as well as at face centers we have particles, and this is the CCP or FCC space filling model. This has a pattern of layers, is often written as ABC type, and metals such as copper and silver, they crystallize in this FCC structure. So this is about CCP. So let's compare HCP versus CCP. Yeah, here we have, this is a ABA. So it is AB type, and this is ABC type. So yeah, this is, you can see, this is HCP type and this is FCC type of arrangement. And coordination number, the coordination number is the number of nearest neighbors. So for a diamond, for a tetrahedral, we have 4 nearest neighbors, so coordination number is 4. For a simple cubic, the coordination number is 6, and for body centered cubic BCC, the coordination number is 8, and for FCC as well as HCP, the coordination number is 12. Okay, so we already studied about the coordination number in HCP, that is 12, and even in FCC the coordination number is 12, where you can see, say if I compare this particle is in contact with the 4 particles in this X plane. So let's suppose this is one plane, and this particle is also in contact with the other 4 particles which are perpendicular. Which particle? The line perpendicular to the previous plane. So here we have 3 mutually perpendicular planes, and each plane is having 4 particles in contact with the centered particle, right? So this centered particle is actually in contact with 12 particles. So that's why its coordination number is 12. Okay, so this is about the structure of the 3-dimensional structures, that is HCP and CCP. So let's solve some question based on that. These are simple MCQs. The coordination number of a metal crystallizing in HCP structure. Just now we discussed the coordination number, how much? HCP as well as CCP, they have coordination number 12. 6 is in simple cubic, 8 is in body centered cubic, and there is no coordination number such as 10. Okay, so let's move to next question. In a hexagonal closest packing in 2 layers, one above the other, the coordination number of each sphere will be. The coordination number of each sphere will be. So here, by seeing hexagonal close packing, we thought that the coordination number is 12, but there is no any 12 option. Okay, so first listen to the question, first read the question carefully. It is given, it is asked that in 2 layers, consider the hexagonal packing in only 2 layers, one above the other, right? So in 2 layers it will be like this. So we have hexagon, right? So in first layer we have hexagon, which is in contact with the 6 particles. So if you consider one more layer above this layer, so this particular, the one which is in the middle, is in contact with the 6 particles in its own plane plus 3 particles above. So 6 plus 3 total, it is 9, right? So in hexagonal closest packing in 2 layers, layer A, layer B, the coordination number is only 9, right? But if you consider the 3D, the 3-dimensional, like 3 layers, A, B and A, so in such case, the coordination number will become 12. Because here we not only consider the particles in above the plane, we also consider the particles below the plane. So that brings out the coordination number as 12. Okay. So 9 will be the answer. Let's move to the next MCQ. In the empty space in hexagonal close packing pattern is. So what is empty space in HCP? HCP, which is having the closest packing of spheres and which is highest efficient packing, which left only 26% empty space. 74% is occupied, only 26% of the space is vacant. So the empty space is 26%. So we learn about the packing efficiency or packing fraction in our in the coming parts. Okay. So this is all about the 3-dimensional packing. One is HCP, which is ABAB type of arrangement. Another is CCP, which is ABC type of arrangement. Okay. So students, in this part we discussed more about the 3-dimensional close packing structures. We discussed about hexagonal close packing structure, which is ABAB type of pattern we got, and we also discussed about cubical close packing structure, and that is ABC type of pattern we got. So in our next part, we are going to discuss more about the voids, as we have discussed in our previous part about the tetrahedral and octahedral voids. So let's locate the tetrahedral and octahedral voids in a unit cell. So keep watching for my next part.